In this DeBacco University video, I'm going to be going over Gibbs free energy, giving you some calculations determining spontaneity. So hopefully you can follow along and develop an understanding for this Gibbs free energy concept represented by the letter G. All right, so when we're looking at Gibbs free energy, we're going to be looking at comparison between reactants and products. We're going to bring in terms like entropy and enthalpy to kind of apply to this equation. So first off, Gibbs free energy, G is the thermodynamic quantity that measures the maximum reversible work a system can perform at a constant temperature and pressure. So I know that sounds very confusing. So let's kind of look at whether that's a positive, a negative, or it's zero value, kind of what that looks like graphically. Maybe that'd be a little easier way to understand it. So again, we're looking at comparison reactants to products. So here's our reactants, Gibbs free energy level, and here's our products. The product level is less than the reactants. Therefore, delta G is negative, meaning that process is those products are going to be lower in Gibbs free energy. In contrast, we could have reactions where the reaction is positive, where the reactants versus the products, delta G is going to be greater than zero, or a positive integer. And here the free energy of the reactants and the products essentially is the same, and that means Gibbs free energy essentially equals zero. So how does this kind of relate, or what's another way we can take a look at this, for example? So we could apply this to an equation. So for delta G, that's change in Gibbs free energy, equals delta H minus T times delta S, or change in Gibbs free energy, which is a delta G, equals the change in enthalpy minus the temperature in Kelvin times the change in entropy. So again, this is where being able to convert units to Kelvin is important in understanding your enthalpy and your entropy and keeping all of your units and all of your areas and portions of this equation nice, neat, and organized. So write things down. Don't try to do everything in your head is my big suggestion for you. And this is going to refer to spontaneity, so those positive and negative Gibbs free energy levels. So when delta G is less than zero, when delta G is negative, the process is spontaneous, or what we call exergonic. So if we're looking here, spontaneous reaction means the products are essentially less than the reactants, meaning this can happen with basically no energy input. We're producing products with less total free energy. Again, energy is being released in this. Again, we're keeping track of it. We know, quote, where it's going, but it's not ending up in the end products, meaning energy is released, meaning this is a spontaneous reaction. Now, in contrast, we see this is a non-spontaneous reaction, endergonic reaction, where delta G is essentially greater than zero. Its energy has to be added. So when you're having to add energy, it's not going to be spontaneous. You have to take energy and add it to the system. And if delta G equals zero, well, that system's essentially at equilibrium. So when it's even, not positive or negative, it's essentially at equilibrium. So if you maybe consider and think about these graphs, it'll help you kind of understand whether something would be spontaneous or not. Of course, it's never quite as simple as just two little graphs, so let's just do a quick little 4 changes summary looking at our delta H and our delta S and how that relates to our Gibbs free energy. So again, where do these delta H's and S's coming from? Let me just flip back here. This goes back to this equation here. H, remember, is the enthalpy. It's got an H in it. And S is entropy. Sorry, I don't have a good way to remember that one. But if you remember delta H is enthalpy, that's going to be key. That's going to refer to your heat. Entropy is referring to your organization. So how do we apply that? Well, when our delta H is positive, it's going to be an endothermic reaction. When delta H is negative, it's going to be an exothermic process. So endothermic versus exothermic. We're looking at our entropy. When delta S is greater than zero, that's going to increase the entropy, and that's things are going to get more spread out and more disorganized. Delta S less than zero, it's going to be a decreased entropy. Things are going to get more organized. So if we kind of line these two up, what are we noticing, or what's occurring? Well, when we have an endothermic reaction and an increase in entropy, delta G will be negative at high temperatures. It'll be positive at low temperatures. So in this example, when this is occurring, this will be a spontaneous reaction only when temperatures are elevated or high. Now, if we still have our exothermic reaction, but now we have a decrease in entropy, delta G will be negative at any temperature, and this process is not spontaneous at any temperature. It's going to require energy input in order for it to occur. Flipping the other way, if we have our enthalpy here of exothermic and our increase in our entropy, delta G will be negative at any temperature, and therefore the process is spontaneous at any temperature. That reaction is basically going to occur. In contrast, now when we've got our exothermic reaction, our decrease in entropy, delta G will be negative at low temperatures, positive at high temperatures. Therefore, this process will be spontaneous only at low temperatures, basically in complete contrast to what we talked about up here. So though this might be initially a little confusing, as we work through some examples, you might want to keep this slide up, do a little quick comparisons, keep track of your values, and hopefully after a few times you go through this, it'll become easier to understand with the aid and help of maybe rewatching this video.